This graph illustrates a core industry crisis. While most sectors have industrialized, construction suffers from flatlined productivity and sharply rising costs for both materials and labor. The Quantum High-Rise project in central London is a massive urban regeneration project that exemplifies these challenges, comprising 3,300 residential units and 1.9 million square meters of commercial space. The development is constrained by a contaminated brownfield foundation with zero space for on-site material storage and a strict mandate to achieve net zero carbon emissions. Net zero is a state where the greenhouse gases emitted into the atmosphere are balanced by an equal amount being removed. Relying on traditional, linear project management and disconnected software tools for a project of this scale leads to schedule collapse and massive cost overruns. Success depends on a completely integrated digital construction stack that fuses data, physical manufacturing, operational logic, and predictive analytics. This shift moves the project away from reactive firefighting and creates a single, unified operational nervous system. The base of this stack is the cloud-based Common Data Environment, or CDE. A CDE is a centralized digital hub where all project participants collect, manage, and share information to ensure data consistency. This environment provides a single source of truth, allowing an internationally distributed design team to collaborate synchronously without the risk of version control errors. Within this hub, the team builds a multidimensional building information model, or BIM. BIM is a digital process that creates a database of the building's physical and functional characteristics, linking geometry to specific performance data. The model incorporates a fourth dimension, time, to visualize the construction sequence and identify conflicts. The fifth dimension connects quantities to cost data for automated estimation and value engineering. The sixth dimension tracks embodied carbon in real time to ensure the project meets its strict net zero requirement. The CDE uses this data to run automated clash detection, identifying where different systems, like a mechanical duct and a structural beam, intersect. This allows engineers to resolve geometric errors digitally, rather than through expensive on-site rework. A multidimensional CDE turns passive blueprints into a predictive digital rehearsal of the physical build. On the physical site, the lack of storage space makes traditional raw material processing impossible. To solve this, the second layer of the stack is Design for Manufacture and Assembly, or DFMA. DFMA is a design philosophy that optimizes building components for efficient factory production and rapid site assembly. DFMA feeds BIM geometric data directly to off-site computer numerical control, or CNC machines. CNC machines are automated tools that use digital instructions to fabricate high-precision components with minimal human intervention. This process allows massive elements, like complete volumetric modular rooms and precast concrete panels, to be manufactured in controlled factory environments. Shifting labor off-site reduces material waste and cuts on-site labor requirements by up to 70%, bypassing local skill shortages. Off-site production enables the structural modules to be manufactured simultaneously with the contaminated brownfield remediation, significantly compressing the project duration. These components are moved to the site using just-in-time, or JIT delivery. JIT is a management strategy where materials are delivered only when they are needed for immediate installation, matching the precise availability of the tower cranes. DFMA transforms the construction site into a high-speed assembly node rather than a raw material processing plant. Choreographing thousands of these precise deliveries requires a system that prevents single delays from causing catastrophic bottlenecks. The third layer is lean construction, an operational philosophy focused on maximizing value by systematically eliminating waste. When top-down, rigid Gantt charts shatter under real-world variables, they are replaced by iterative lean flow cycles that connect design and manufacturing. The primary tool for the Quantum project is the Last Planner System, or LPS. The Last Planner System is a collaborative planning framework where those responsible for executing the work make the final commitments on scheduling. Traditional scheduling often fails because it plans from the top down, only uncovering constraints like missing materials or design gaps after work has already stopped. The Last Planner System uses a rolling 6-week phase schedule to identify these constraints, such as crane access or design ambiguity, well in advance. The team tracks percent plan complete, or PPC, a metric that measures the reliability of these commitments and assigns responsibility for removing constraints weeks before work begins. Integrating lean logic with BIM data shifts project management from reactive firefighting to proactive constraint removal. To maintain precision, the project needs a feedback loop that connects the digital plan to the site operatives. Workers use extended reality, or XR, to project the digital model onto the physical building. Extended reality is an umbrella term for technologies like augmented reality that merge physical and virtual environments to provide real-time data overlays. This overlay enables millimetric installation accuracy on the first attempt and provides managers with instant quality control verification. The final layer of the stack is AI predictive analytics, fed by the Internet of Things, or IoT. The Internet of Things is a network of physical sensors that collect and transmit real-time data from the field to a central system. These IoT sensors pull continuous data from crane operations, weather forecasts, and supply chains. Machine learning algorithms process this data using a Monte Carlo simulation to forecast project timelines, modeling the probability of different outcomes. The AI analyzes current performance trends to forecast delays and automatically suggests supplier shifts that preserve the schedule. Combining XR, IoT, and AI creates a self-correcting feedback loop that binds the physical build to its digital simulation. This completed 4-tier stack operates as a single, unified operational system. We define this integration as the LBX synergy, the combination of lean construction, BIM, and extended reality, optimized by artificial intelligence. Through this stack, BIM designs the building elements, lean schedules their arrival, XR verifies their installation, and AI monitors the systemic risk. The initial constraints of the quantum project, the productivity gap, the constrained site, and the carbon targets, all required a departure from traditional building methods. The stack resolved these hurdles by transforming physical limitations into programmatic logistical problems. Adopting this integrated stack allows the construction industry to bridge the productivity gap, turning chaotic sites into predictable and sustainable engines of urban regeneration.